So where we're going to look now is our electrophilic additions, which again, we categorize out into two different places. This is going to be the one brief video you're going to see on strong acid additions, which is primarily chapter 11. Alkenes or alkynes are non-polar, so they are not very reactive. So what we need is something to get them going. And so this is where we see our strong acids, because as being strong, they force H plus out there, which now gives us something to neutralize the electrons of our alkene or alkyne. And then chapter 12 and again 24 does the electrophilic addition. So again, those things that you need to be looking for as far as patterns. In those patterns, we're looking at a nonpolar pi bond. That nonpolar pi bond has electrons in it, and in fact, it has 2 electrons. So when we're talking about the reactivity, we're looking at it act as either a nucleophile, because it's looking for a positive nucleus, or it's acting as a base because it is sharing electrons with a hydrogen. And again, because it is a weak or low reactivity, it's a weak base and a weak nucleophile. So we need strong acids to go through and initiate this reaction. So if we're looking for those differences in charges, what we're really saying is we have a strong negative and a strong positive. And it is that association that's leading to the chemistry here. When we're looking at our acid chemistry, deciding where everything should go and balance out is largely going to be due to the reactivities of the individual pieces. So what are those reactivities? What am I talking about? Well, because it's a strong acid, the most reactive thing here is this H plus. And for all intents and purposes, whatever this nuke is as a negative is a secondary feature, which then means when we draw out our reaction, the acid picks up or reacts with the pi bond first, which would generate a carbocation as an intermediate. The nucleophile being, or the negatively charged species here being labeled currently as a nucleophile, is relatively stable on its own. And we know it's stable because this was a strong acid, which means it does not need to immediately react with the carbocation or the forming carbocation. Where do we decide to place that hydrogen? Well, because we don't, or we know we need to form a carbocation, it's now deciding where should we place it. Should we place the carbocation out there? Or should we place it here, right? And so deciding between those, we would have to know something about carbocation stability and acknowledge that the secondary carbocation is more stable than the primary, and that's what's going to drive the chemistry. It's that charge, which comes from our structure and our differences in electronegativity. So understanding that really helps us predict these reactions, right? And that's where almost all of our reactions in chapter 11 go. So as an example, how would we know if we were looking at this structure that our pi bond was going to act as a base? Right? And that is in itself kind of a misleading question, because that puts the focus of this chemistry on the alkene. Well, is that an appropriate focus? Should our focus be on the alkene? In a standard organic chemistry textbook, you'd say, well, yeah, because it's organized the alkene chapter. That's the problem with that organization. You've removed an understanding of the reagents, okay? Before you took any chemistry class, you had hydrobromic acid thrown at you or alkene thrown at you. Which one were you going to panic about more? Probably the hydrobromic acid. That's because it's the more reactive one. That's the one that we should put our focus on. That's where our chemistry needs to be. So when we look at this reaction, we're looking at HBr with a positive hydrogen and a negative bromine. The electrons come out. We put our hydrogen where we form the more stable carbocation. We could then have the bromide come in and react, and we would end with our final product. So again, if we understand something about the chemistry of where the electrons want to go or can go, okay, and personifying things is usually a bad idea, okay, we can get a better understanding of how our reactions work, right? And that's your focus here. It's not just memorize the reagents, because the problem with that is you're probably going to also memorize the starting structure, and the starting structure is undoubtedly going to change, which means you won't be able to get the answer right. Okay, so look for that chemistry and how it moves. To that end, we've got an example question for you to go through and solve. So I'll give you a hot second to get this one figured out. Yeah, I didn't pause the video, actually. I was just seeing if you would solve it. Right? So now you can go ahead and solve it. If you haven't, that means hit the space bar, click pause, do something like that, and come up with an answer. Right? If we were to go through and do this now, because I'm assuming that you've gone through and done it, we would again acknowledge that our hydrogen was the most acidic. The bromine would be our negative. How do we go through and align this? We're going to take the electrons from the pi bond, react with our positive hydrogen. The electrons go to our bromine. We would have a pi bond. We would place our hydrogen here, and we'd form a carbocation here. Okay. We could then say, well, the bromine comes in, Br minus comes in, and we would get something along these lines with the bromine there and our pi bond there. Right? This is where OChem 2 becomes a little bit more challenging. Should it stop there? Right? In OChem 1, we might have just said, we'll just do it once and see and be done with it. In OChem 2, you're expected to evaluate should it continue. Well, in this case, it reacted with a pi bond. Is there still a pi bond? Yeah. So that means it reacts again. So it'll react with another hydrogen going through to produce another carbocation where that bromine is located. And then our bromide, our second bromide, can come in and react. This does beg some questions almost immediately. Where did the second HBr come from? Where did it come from? It came from the solution. You might say, well, but it only says there's one right here. Doesn't that mean there's only one? No, actually it doesn't mean that. Okay? When we run a reaction, we don't run a reaction with single molecules. We're running these reactions with hundreds of molecules. And hundreds was a way low estimate. Okay? Remember, you're looking at 0.1 moles, so 6.02 times 10 to the 22nd molecules. There's a massive number of molecules here. Okay, so you need to always be thinking about, well, what if there was a whole lot of this? Okay, and only in cases where we get very, very, very subtle differences in energy do we really need to be going, oh, okay, well, it only does it once. Right? It's very rare. Right? If we were to go through and look at this, we could predict something about reactivities. This is a vicinal. I'm going to call it an sp2 carbocation, which we should remember from OChem 1 is incredibly unstable. So we might say that that first step is impossible. Right? It turns out it's not impossible. This is where you give it enough heat, it does work. Right? That structure is now so incredibly reactive that it continues to react. Right? And that's why we get the double addition of that bromine. Right? And technically the hydrogen as well. So look at your structures, think about that continued chemistry, which then brings us to the next example. Right? How is this one different? Well, again, we still have a strong acid. That strong acid is our H2SO4. What we should again remember from first semester, is that we have the sulfate anion, and the sulfate anion is a horrible nucleophile because of all that resonance stabilization. That's where H2O comes in as our nucleophile. So when we're looking at these reactions, it doesn't have to be the same species. It can be split across multiple ones. So if we were just to say, predict this out and run all of our mechanistic steps, we might go through and say, well, we'd end up with that. Again, we might also go through correctly and say there's a pi bond, and that continues to get us to here. Fantastic, right? If you tried that problem and got there, excellent work. you're still wrong, but excellent work. Okay? So why are we wrong? Okay? Well, what we've created there is what is known as a hydrate. And hydrates are incredibly unstable. They are so unstable that they immediately revert to the ketone form. Okay? And it depends where the hydrate is located, but in this case, it's going to revert to a ketone. And you might rightly get a bit irritated and be like, but I didn't know that that was a hydrate, and I didn't know that that had to go to a ketone. That may be true, but you should have acknowledged right here that this step, the one that you went to make the hydrate, was wrong. Okay, and wrong in loose terms. What you should have acknowledged that this structure right here is an enol. And the enol, ene, alkene, all, alcohol, the enol is highly unstable and immediately tautomerizes to the ketone. We don't have to go through the hydrate structure at all, and we'll still get to that ketone form. Okay, so you have to be thinking of those pieces. That process is our keto-enol tautomerization. So good for you if you happen to watch the and I think I butchered the spelling again. If you watched that intro video where I said the tautomerization was important, here it is. Shows up pretty darn quickly. Okay, so we will be constantly seeing that keto-enol tautomerization. We have to remember it. You have to be thinking about it. So while our addition reactions with acids tend to be more straightforward, there are plenty of cases where they can go a little bit sideways, and you got to kind of watch out for them. Okay. So what now makes this second semester? Okay, so we're going to make this second semester by throwing in another pi bond. Okay, so again, what I want you to go through and do is attempt this question. Strong acid, HBr, instead of it being a triple bond, it's now 2 pi bonds. And go through and attempt this. That means pausing that space bar. Okay, and I'll assume that you've gone ahead and done this, and I'm going to go through and say that you came up with this for a final answer. For those of you saying, no, I didn't, good, you shouldn't have come up with that for a final answer. Okay. When you came up with that as a final answer, you treated both of these pi bonds as independent structures. Okay. They aren't independent. They aren't independent because we have a resonance contributor within that, which I will show you here, assuming my computer connects. We have the ability for resonance. That resonance is going to affect the outcome of our individual reaction. So how does it affect it? Well, first and foremost, let's run the reaction and let's see what it does. In the very first step, our pi bond reacts with the hydrogen. For those people saying, why'd you pick that pi bond and not the other? It's a good question. You tell me with this question. When we draw out that product, we will get the carbocation there. For those people saying, why'd you not draw the hydrogen? Well, if I show the hydrogen, I then technically also have to show those. And I don't know about you, but that looks ugly. So I'm not going to do that. So I'm just going to imply it. And we, lest we forget, also have that pi bond. So what we now have is a carbocation that has resonance capabilities, which means this structure is shuttling back and forth between a carbocation at the end versus on the inside, right? And for those people now trying to decide, well, where should we continue our reaction? That's a good question. I really like that question. To decide that, we would need to evaluate something about the stability, potentially, of these two materials. Okay? In that stability, we're looking at carbocation stability. So back to OChem 1, which one is more stable? Secondary is more stable than primary. We would expect the top one to win out. So if the top one wins out as our overall resonance contributor, we could now have the bromide come in, Br minus, attack our carbocation, and we would have the bromide here. Okay, decent. But let's just say for giggles because that's what we do in OChem, we just laugh, that it went this way. Okay? Now what would the result be? Now we've got to ask the same question that we asked with our carbocations. Is there a difference in stability between these two structures? Well, the most reactive thing between those two structures is the pi bond. So when I'm looking at pi bond stability, more substituted is more stable, which then means the orange one is more likely to form than the black one. Think back to our carbocations. We said the red one was more likely to form than the blue one. Anybody notice a bit of a paradox here? Yeah, they conflict against each other. And being able to understand when and why that conflict appears becomes challenging. And that's one of the big aspects in second semester OChem, is how do we deal with that apparent conflict? Right? One of the ways that we could go through and do that would be to draw energy diagrams. Okay? So I am going to go through and draw the energy diagram here, but what I'm also going to direct you to in that upper right-hand corner is there's a play posit called kinetics and thermodynamics, and I'm going to ask that you watch that now. One of the sections of that video addresses this very reaction. I think I addressed 3 more reactions in there that we haven't talked about yet. Right? But what they're trying to get you to think about is this balance between kinetics and thermodynamics. And that is something you should remember from Gen Chem, particularly Gen Chem 2. Right? And that's the one that everybody decided to ignore. And really, the summary of Gen Chem 2 is this: reactants, products, activation barrier. Right? And for everybody thinking, well, what about ice charts and all of that? Well, that ice charts was dealing with this section, the difference in energy between reactants and products. And that was known as thermodynamics. And there was a small section, depending on how your class organized it, that also addressed that activation barrier, which was the difference in energy between the reactant and that activation barrier. And that we knew as kinetics. Holy crap, that's where the title of the video is coming from. It's addressing that balance between kinetics and thermodynamics, and that's a lot of what you did in 152. Okay? And it was really centered on an energy diagram and how to interpret it. So a lot of the times we will be coming back to these energy diagrams. I want you to use them to think about, to manipulate your reactions, to understand when this kind of balance is going to come into play. A lot of it is hand wavy in OChem, and that's largely because we don't want to have to deal with numbers. Instead, we decide to take some rules and apply those rules. So let's go ahead and start with this. We've got our reactant. We'll pick an arbitrary middle spot. Our intermediates, and this one's a bit disingenuous because this makes it look like there's 2 intermediates. There's really only one because it's resonance. Okay, whoops. Let's draw that as an I. We have the blue intermediate and the red intermediate, and then we'll call it blue. Sorry, I want to switch. Oh man, we're just gonna have to stick with it. Product, blue product, and red product. So what I'd like you to do is, again, hit that pause and attempt to draw an energy diagram. So now that you're back with me, let's go through and take a look at this. Our intermediate should be higher in energy than our reactants because they're charged. Okay, so let's go through and pick, say, the red one. The red one should be the lowest energy because we're looking at a secondary versus a primary. So that secondary will be higher in energy than our reactant, but it will be relatively low. So that's our intermediate. The blue one, being a primary intermediate, will be higher than the red one, still higher than the reactant. We go through and move to the product side of it, and this one becomes more challenging. On the product side of it, we have one less pi bond, so we should be lower in energy than our reactants. Between these two products, this one was more substituted, and because it was more substituted, it is going to be lower in energy. The top one was a less substituted pi bond, which makes it higher in energy, still lower in energy than our reactants. Product and product. So now what do? We just kind of connect the dots. We can put in some rough activation barriers, and we've got our overall reaction kind of running out. And this crossover, this is what creates the kinetic and thermodynamic argument. Okay? When our two energy diagram paths cross, now we have that kind of dilemma coming out of this. So if we went through to look at this, we would expect the activation barrier for the red one to be lower because the intermediate is lower in energy. That means that that reaction happens faster, which means when we get to the product, that product should form first because we're talking about a speed. That would be a kinetic argument. Okay? If we took a look at the blue product, since it is lower in energy than our red one, the delta G for the blue one is much larger and therefore more exothermic and therefore more favorable, would be the thermodynamic product. So which one should win? Well, a lot of that which one is going to come out based off of reaction conditions, reagent conditions, and the exact energies of these pieces, some of which we can draw parallels to in later cases, some of which we can't. Okay? So we'd have to rely on some kind of external knowledge, and that's where OChem 2 comes into play and sometimes becomes a bit unfortunate. You're just expected to memorize some of these reagents. So let's think about some conditions first that could force one. What happens if I increase the temperature? Okay, if I increase the temperature, I can now clear the activation barrier. Okay? And when we think about that, we might say, well, an increase in that means I should expect the thermodynamic product because I can now clear the activation barrier for it. Okay? So higher heat tends to form the thermodynamic product. And one of the arguments that people will make is that because we can clear that activation barrier. That's part of it. That's only half of it. Increasing the heat actually addresses this activation barrier. What I'm coloring in is an orange one. Even if I go to high heat, I'm still going to form the red product first. It's the kinetic product. It's always going to have a lower activation barrier. Okay? But if I provide more heat, what happens is that product can now reverse. And if it reverses, some small amount is going to make it up on the thermodynamic product scale. So high heat and long time, I get thermodynamic. Okay? And it's because of the reversibility now of the kinetic. So if I want the kinetic product, drop the heat, run the reaction short times. Okay? And that should force a more kinetic product to form as opposed to the thermodynamic. Okay? One of the key aspects in that was, again, addressing the reversibility of that step. Well, what if the reversibility is so thermodynamically or kinetically irreversible that I can't reverse it? Well, now it's going to be a kinetic-only product. It doesn't matter the temperature or the heat because kinetic product is the one that's going to form faster. So we have to address kind of those balances. Some of it is temperature, some of it is time, and some of it is the reagents being used. So we have to consider all of those pieces when we're looking at our reactions. This is really just the first case that this appears, so I want you to be familiar with it, and it really pops up with our conjugated pi systems, and this is the simple version of it. Okay? Wow. So if we were to look at these reactions or this particular reaction, what might happen with this particular conjugated pi system? So one of the things that you should remember from OChem 1 would be when we have a radical reaction. One of the key signifiers of a radical reaction is roar. Roar is going to cause these to move into radicals. Why does that become particularly challenging? That looks like a weird, unimpressed face, right? is that now we can do radical reactions where we're forming a bond. So we could form a bond there. We could form a bond there. So we've got lots of different places that we could form a bond, which means what we end up getting out of this is a mess of cross-linked alkanes, okay? What you might remember this as, depending again on your class and how much you remember of OChem 1, is that we're using or making a polymer. Okay? We're getting the formation of a polymer coming out of this. Okay? And a lot of that was driven by that extra reactivity of ROR. We will address polymers in more detail much later in the semester, probably as a supplemental video. Okay? So what happens if we say got rid of ROR? Well, now nothing should react, right? Right? Except something to consider. Can't I draw a resonance where I have a positive and a negative? Right? And if you did that, that's fantastic. That's a really good job. We do have those positives and negatives popping up in here. But as we started this kind of sequence out, the alkene and the alkynes are nonpolar pi bonds. They don't resonate very much, okay? Which means we don't get a lot of that positive negative, which means we really don't expect a product, okay? So at the end of this, we might say, well, no reaction, right? And of course, that's a dramatic pause, because one of the things that in that analysis, I didn't actually say anything about how they could move or align. Couldn't I have moved or aligned it to look like this? Well, it was, so what? Okay, so you've moved and aligned it. We still don't have those positives and negatives. We don't have anything to initiate this. We would expect, again, no reaction. Until somebody did it, and we got that, okay? That's now weird. Why would that happen? What's going to cause and allow that to occur? Okay? That reaction, because we expected it to not happen, and it did, now gets named. It's an exceptionally famous reaction, lots of stereochemistry, lots of regiochemistry. If you're in the lab, you're doing your first lab is kind of looking at some of this. And there is an answer video that you can go through and watch. There's also the question video on thinking about how this reaction could work. This reaction is named for the scientists that discovered it and studied it extensively, and that's Diels and Alder. So it's known as a Diels-Alder reaction. I would list their first names. I think it's Otto Diels and Kurt Alder. I may have got them backwards, but I think that's right. And that's an important reaction that largely comes out of these conjugated pi systems. It also brings in a terminology of cycloadditions, okay, which is a large part of the oxidation reactions in chapter 24. So chapter 24 really digs in a lot into our Diels-Alder reaction because it's an example of a cycloaddition. Cycloadditions are heavily dependent on molecular orbital theory to explain a lot of the reactions and dynamics behind them, but you can kind of cheat and just memorize stuff to get out of that, and that's addressed in that video also. Depending on your level of OChem knowledge or where you're going to end up, you may see that in more detail later on in your life. If you're just here to get a prerequisite, you probably won't see it again, okay? But that's really digging into molecular orbital theory. Neat stuff, but we're not going to address it, at least not in this video. And with that, thank you for watching this one. We are done with our acid